In this lesson, we're going to introduce the important concept of exponential growth. To help you gain a proper appreciation of what exponential growth actually is, I want to give you 3 questions to start off. And you're going to get the most out of this if you actually try to pause and guess the answer to each of these questions. For the first problem, I want you to imagine that we started off with just 1 coin. And then at the end of every single day, I'm going to double the number of coins you have. So on the second day you'll have 2, and then on the third day you'll have 4. If I kept doing this for a whole month, how many coins do you think you're going to have at the end of the month? Now for the next problem, I want you to imagine that you started off with a sheet of paper. Now assuming this is just an ordinary piece of paper, I want you to imagine folding it in half. If you fold it in half, you're actually going to double the thickness of the paper. But after you've folded a piece of paper in half a few times, it gets really difficult to keep folding. So instead, I want you to imagine just stacking 2 pieces of paper on top of each other. I want you to imagine that we took this piece of paper and then we just continued doubling its thickness 36 times. How tall do you think the stack of paper would be after 36 doublings? And now for the last question. I want you to imagine that we started off with a single pencil. I then want you to imagine repeatedly cutting the pencil in half. Now the question I'm asking here is, how many times can we actually cut this pencil in half before we're left with just a single atom? Problems like these 3 are the exact kind of problems that exponentials were designed to solve. So as I've written here, the thing that's common to all 3 of these different problems is that all of them have a repeated multiplication somewhere. In this one we're multiplying the coins, in this one we're multiplying the stacks of paper, and in this one we're multiplying by half to half the size of the pencil. Now if you want to get the absolute most out of this lesson, this is the point where I suggest you pause and try to guess the answer to each of these 3 questions. But at this point, I'm actually going to show you how to answer them. So let's bring out a piece of paper and try to find the answers to each of them. So let's start by trying to solve this coin problem over here first. I want you to imagine that we started with the number 1, and we're just going to keep doubling it over and over again. So we start off with 1 coin, as you can see here. But then we just multiply it by 2, so we end up with exactly 2 coins, as we can see. After that we multiply by 2 and we end up with 4, and then we multiply by 2 again and then we have 8 and then 16 and so on. So we want to figure out how much we have after exactly 30 doublings. Now if you think about it, this number 2 over here is the same thing as 1 times 2. And then to get 4, we have to multiply by 2 again, so we end up with 1 times 2 times 2. But as we know, if we multiply something by itself, that's the same thing as raising it to the power of 2, so we can rewrite this as 1 times 2 squared. Now after this, we can multiply by 2 again to get the number 8. So instead of having 1 times 2 squared, we're going to end up with 1 times 2 cubed. And once we've seen this, the pattern along this bottom row over here is really easy to see. We just keep raising the power by 1. So if we want to double the number of coins you have 30 times, then after 30 doublings, you'll end up with 1 times 2 to the power of 30 coins. And then the only question left to answer is, what does 1 times 2 to the power of 30 actually equal? Well, that's a question best left to a calculator, so let's actually type this into a calculator. Now, this is not a mistake. You should actually try this with your own calculator if you don't believe me. But we actually end up with over 1 billion coins. Not 1 million, but 1 billion coins. Now this is actually part of what makes an exponential exponential. An exponential is something that grows incredibly quickly. So as you can see, starting off with just 1 coin, you end up with well over 1 billion coins if you keep this up for 30 days. So now for the paper problem, we're going to do the exact same thing, but this time we're going to start with a different number. because the thickness of a single piece of paper is approximately 0.1 millimeters, or 0.039 inches. So to keep things simple, I'm going to actually write the answers out in meters, because I can tell you right now that the answer is going to be way bigger than a meter. So a single paper is 0.00001 meters, and if we were to double that, we'd end up with 0.0002 meters. But as we already saw, we can just rewrite this as 0.0001 meters times 2. Now, following the same pattern that we had up here, the only difference is that instead of starting with 1, we're starting with 0.0001. So if we keep doubling, we're just going to have to keep multiplying by 2. So to work out how much we have after 36 doublings, we just multiply 0.0001 by 2 to the power of 36. And now, just like before, we can figure out the value of this by putting it into a calculator. And now I'm going to say this one more time. This is not a mistake. The answer is really 6 million meters. You start off with a piece of paper that is 0.1 millimeters, and you end up with over 6 million meters of paper if you were to double 36 times. So just to give you a comparison that can help you wrap your head around this number, the radius of the entire Earth is 6,371 kilometers. And the height of your stack of paper is actually 6,871 kilometers. So this is a 2-scale, approximately, picture of the Earth and your stack of paper. Your stack of paper would literally be more than half the diameter of the Earth. In fact, if you doubled one more time, it would actually be bigger than the entire planet. And now finally, we just have to tackle the pencil problem. Now, if I'm being entirely honest with you, the first time I ever saw this question, I thought that you would need to cut the pencil around 1,000 times. Now, the size of a single atom is at least 0.1 nanometers, so I'm going to use that as the size of our atom. Now, just in case you don't know how big 0.1 nanometers is, that's going to be 0 with 9 zeros and then the 1. Now, instead of writing numbers like this, we can also write them in scientific notation. And that's generally a good idea when you're dealing with anything to do with exponentials. So therefore, a better way to write this would be 0.1 times 10 to the minus 9, as I've done here. Now, let's go with my first guess. Let's imagine we actually did divide this in half 1,000 times. Now, to figure this out, we're going to need the size of a standard pencil. So when I looked this up, I got a figure of 19 centimeters when you buy the pencil brand new. Now, 19 centimeters is the same thing as 0.19 meters, and then we're going to half this 1,000 times. So we're going to multiply it by 1/2 1,000 times. So that's 1/2 to the power of 1,000. Now, just in case you find this confusing at all, we've just done the same thing we did above. We started off with some value, and then instead of multiplying by 2, we've actually multiplied by 1 on 2, because we're actually halving the length and not doubling it this time. But without using up any more time, let's go ahead and put this into a calculator. Now, most calculators you try will actually write down the number 0 if you tried this. You should actually pick up your calculator and see what it does. So I actually needed to go to a computer to actually get this value at all. But as you can easily see, this value has 300 zeros before this first one, and therefore it is way smaller than the size of an atom. So 1,000 times is too many. So we're really going to need to drop our guess by a whole lot. So how about we try guessing 100 times? What if we cut the pencil in half 100 times? Well, into the calculator this goes. This time, the value we get is approximately 1.5 times 10 to the minus 31 meters. Now that is also way smaller than the size of an atom. The size of an atom is 10 to the minus 9, and this actually has 30 zeros before we get to that 1. So we can't even cut a pencil in half 100 times. 100 times and it's already way smaller than the size of a single atom. So how about we try 10 times? Surely we could cut a pencil in half 10 times, right? Well, how about we ask the calculator again? So at least some of our sanity is restored here, because this is actually bigger than the size of an atom. Notice that the size of an atom has way more zeros than we have this time. Now, despite the fact that this is bigger than the size of an atom, I still want you to take note of how small this number is just after 10 cuts. Now, this would be a millimeter right here, so we have something like 0.18 millimeters. That's incredibly tiny. Now, if you want something to compare this to, remember that this is the thickness of 2 pieces of paper, and this is approximately the same as this number over here. So after 10 cuts, a pencil is as thick as 2 pieces of paper. Now, you could continue this process for as long as you wanted, but I'm just going to go ahead and tell you that the answer is approximately 30 cuts. Now, if you're anything like I was when I first started studying maths, you would have got the answers to all 3 of these problems completely incorrect, because I totally did. Later on, I'm going to show you a technique to figure out exactly how many cuts you'd need to solve this problem, but these problems are already problems that we can solve. But any function that has this form over here, where you've got some number multiplied by another number to the power of another number, that's what we mean when we talk about an exponential function. So that finishes our problem. So I'll copy out the answers to the main page, and then I'll write down a little bit about these exponential functions. So these answers are really surprising, and as I said, they're all examples of exponential growth. So to make it clear, an exponential is a function in the following form. So you start by picking some number a, which has to be a real number, and it's going to tell you how fast your thing is growing. And then an exponential function just has the form a to the power of x. So f of x has to be a to the power of x, where a can be any number you like. It turns out that exponentials are a great way to model anything that grows by multiplying by some fixed number. Now, whilst this idea of repeatedly multiplying something seems like it's a really specific idea, it actually applies to a lot more things in nature than you'd actually think. So how about I give you an example of one, so you can actually see this for yourself. So this is a bit of a chunky problem, this one, but let's read it together. I want you to imagine that you had a bacteria in a Petri dish, and it's going to grow to be 1.3 times its old size every single day. If you started with 2 centimeters squared of the bacteria, how large would the dish need to be to allow for 15 days of growth? So you can imagine that this Petri dish over here houses this sample of bacteria, and it starts at 2 centimeters squared. And you need to figure out how big the Petri dish needs to be to contain this bacteria after 15 days. Now, if we were to actually form an exponential model, then I want you to understand that the Petri dish starts off with 2 centimeters squared of bacteria. So I want you to imagine making a function, f of x, that represents the amount of bacteria after x days. So x is the number of days that have passed since the first day. Well, on the first day, we started off with 2 centimeters squared of bacteria. So let's start by writing out the 2. Now after 1 day, we're multiplying this by 1.3. So that means we need to multiply this 2 by 1.3. Now if 2 days pass, we multiply by 1.3 again. And we keep doing this for the number of days that have actually passed. Well, if we combined all of these into a single multiplication, we could rewrite this as 1.3 all to the power of x. And therefore, the function that predicts the amount of bacteria in our Petri dish after x days is 2 times 1.3 all to the power of x. Now you can see that this 1.3 to the power of x is an exponential function. And as you know, it's perfectly okay to multiply functions by constants, so we've just done that here. And if this is an exponential function, then the value of a, which is our growth factor, is actually 1.3 in this particular case. So therefore, to find the amount of bacteria in our Petri dish after 15 days, we just need to replace this x for the number 15, because we want x to be equal to 15. And now the right-hand side is just a number, so we can easily just plug it in to a calculator. So therefore, after 15 days of growth, the Petri dish would need to be at least 102 centimeters squared to contain all of this bacteria. Now, if you had an actual, real sample of bacteria, it wouldn't actually be possible for it to keep exponentially growing like this. After some amount of time, the bacteria will run out of new food and resources that it can use to keep multiplying. In fact, for a real sample of bacteria, it'll actually take some time before it even starts growing, but once it starts growing, it will do so exponentially until it runs out of food or resources to keep growing. It turns out that bacteria is not the only thing that grows exponentially. For example, the number of people infected during a pandemic also grows exponentially, and the number of humans on the planet grows exponentially as well. There are many, many things that follow an exponential pattern, and you'll see many of them as you study more mathematics. But I think that just about completes our example, so let's go ahead and summarize the lesson. This was a lesson about exponential growth, which is something that arises anytime you repeatedly multiply any quantity. To properly explain exponential growth, I started with 3 examples that I think had really surprising answers. If we doubled the number of coins you had every day for a month, you'd end up with over 1 billion coins. If you doubled the height of a stack of paper 36 times, your stack of paper would be bigger than the radius of the Earth. And finally, if you kept cutting a pencil in half, after 30 cuts, your pencil would be so small that it would be smaller than a single atom. As we tried to actually figure out the answers to these problems here, we managed to see that all of them followed this exponential behavior. So we ended up defining this exponential function, where a is a real number, to allow us to model situations exactly like this one. For this first problem over here, our a value is actually going to be 2, because we're doubling every time. And the a value is also 2 for this problem as well. But the a value for this problem is actually 1/2, because we're actually halving the size of the pencil. So this a value over here actually tells us the rate at which our quantity is growing. And this x over here tells us the number of times we've actually let it grow. As we stated, lots of different things are actually modeled by functions of this form. And it turns out that this is actually one of the most important functions as you study calculus later on. A proper understanding of the exponential function will allow you to predict things like this without even really breaking a sweat. But I think that this is actually a good ending point. So at this point, I'm going to say that you've been sufficiently introduced to exponential growth. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.